So it's my pleasure to introduce today's seminar speaker, Dr. Nora Shipp. Nora got her PhD from University of Chicago, and then last year moved to MIT as a postdoc there. She's an expert in tidal streams and Milky Way dynamics, and interested in understanding and constraining dark matter as well. And so I think that's what she's going to talk to us about today. So I'll let her take it away.
Thank you. Thanks for the introduction and for having me. So I'm going to be talking about some of the work that I've done on stellar streams. So first, I'll start out with a little bit of an intro to streams and especially a focus on some of the observational work we've done over the past few years on building up a population of streams in the Milky Way with complete 6D position and velocity measurements. And then for the second half of the talk, I'll mostly focus on this recent paper that I put on the archive just a couple weeks ago, comparing this population of Milky Way streams to streams in cosmological simulations. So in particular, I will both ask and answer the question, is there a too big to fail problem in stellar streams? Okay, so for anyone who isn't already familiar with streams, stellar streams are the tidal remnants of globular clusters in dwarf galaxies that are disrupted as they orbit around a host galaxy like the Milky Way. So in this nice simulation here, you can see these three streams getting gradually torn apart until they form these long streams of stars stretched out across the sky. And even in this video here with just three streams, you can see we have a range of interesting morphologies. We have some streams that have sort of surviving partially bound progenitors, whereas some streams are just the tidal tails where the progenitor has been fully dissolved. So over the past few years, we've really been building up the population of Milky Way stellar streams. Now we know of around 100 streams in the Milky Way. We've also been improving the quality of other observations, getting measurements of their proper motions from Gaia and their radial velocities with various spectroscopic surveys. There's a lot of really exciting science that we can do with stellar streams. So we can use them to measure the local gravitational potential and the local distribution of dark matter. So because of the way that streams form, the way they're disrupted by the Milky Way's potential, and the fact that they stretch in some cases tens of kiloparsecs through the Milky Way's halo, they're very sensitive to the local gravitational potential. So we can model them to measure the mass or the shape of the Milky Way's halo. On smaller scales, streams are also sensitive to substructure in the galaxy. So they're sensitive to very massive substructure like the Large Magellanic Cloud or other satellites of the Milky Way. They're also sensitive or predicted to be to very low mass substructure, including dark matter halos that have no baryonic component and can't be detected using usual methods. So just because these systems exist in the halo and stellar streams are orbiting in the halo, we expect that sometimes they'll interact gravitationally. And these low mass subhalos can leave behind distinctive density perturbations, just like the ones that you see here, that we can use to indirectly infer their presence just by studying the density of stars along stellar streams. So this is one of only a few methods that's been predicted to give us measurements of these really low mass halos, which can enable us to constrain the minimum dark matter halo mass, which is very sensitive to different properties of the dark matter particle. We can also use it to study, use a population of streams to study what the overall mass function and radial distribution of these low mass subhalos are. Here's just a figure from LSST dark matter white paper where we made an approximate prediction of the mass of low mass subhalos that should be detectable from one gap in a stellar stream. So the green here is with 10 years of LSST data. The y-axis here is the total mass of this subhalo. So depending on the surface brightness of the stream, we expect to be able to see subhalos down to even 10 to the 6th or maybe lower, which can enable very strong constraints on things like the dark matter particle mass. And finally, streams also tell us a lot about galaxy formation. So they provide a sort of snapshot of the accretion history of the Milky Way. So we can use them to learn about the buildup of the Milky Way stellar halo, about the processes of tidal disruption that satellites undergo in the Milky Way, and generally to just learn about this process of hierarchical structure formation. Okay, So in order to do any of this exciting science, we really need a large population of very well-studied stellar streams, and we really need complete 60 phase-space measurements. So for example, if you want to model the orbits of streams to measure the mass of the Milky Way, or even if you want to determine whether some density variation in a stream comes from a low-mass subhalo, it's important to have a good understanding of the full 60 kinematics. So over the past few years, my collaborators and I, including Ting, who's here, have been working on observing a large population of stellar streams. So there are other groups that have been working on this as well at the same time, but I'm going to focus on some of the work that we've done. And this is also the data set that I've used in my recent paper, which I'll talk about in just a little bit. So this started with the discovery of many of these streams in the dark energy survey. So DES is a very deep, wide area photometric survey. Here's the DES footprint. And essentially to search for these streams, we use the fact that we know that they come from globular clusters in dwarf galaxies. So they tend to have very old and metal poor stellar populations. So in color magnitude space, we can create filters to select out stars that are more likely to belong to these populations. That's what I'm showing in this movie on the left. Here, I'm looking at just a small patch of the sky around one globular cluster. And it's the same data that's shown in color magnitude space here. This is a spatial plot. And then I'm shifting this filter in distance modulus so that you're looking at these stars at a range of distances in the stellar halo. And you can see when the filter lines up with the data from this globular cluster, it really comes into focus here, and then it fades away. So this is what we use to detect these streams in DES. Here on the right, I'm doing exactly the same thing, but with data across the entire DES footprint. So darker is higher density. So these dark linear features are the DES stellar streams. So within DES, we discovered 11 new stellar streams and improved observations of 4 previously known streams. So it's a total population of 15. And so the DES data is really great for searching for stellar streams, and this will be relevant later as well. So I just want to emphasize its very wide area, very deep, and very precise photometry. So in addition to having this exciting new population of streams, they're also very well observed streams that are very great for doing all of this science that I described earlier. Okay, so we were lucky that soon after we discovered these streams in DES, Gaia DR2 came out, so we've been able to measure the proper motions of most of the DES streams. And here, this figure on the left is summarizing some of these measurements. So this, again, is the DES footprint on the sky. The black lines are stream tracks. Blue arrows are the proper motions, the magnitude and direction of the proper motions, which is the motion along the sky. And so one interesting thing that we saw here is that for a stream on an unperturbed orbit, you would expect its direction of motion to line up with its track on the sky. So as it's disrupting, it sort of gets stretched along its orbit and should continue moving in that direction. But what we see here is that many of these blue arrows are offset from the black lines. So even with these pretty early velocity measurements of these streams, we learned that they're actually a lot more complicated, more interesting than we had previously realized. And in particular, a lot of these perturbations we found later, and I'll talk about it just a little bit, are due to the presence of the Large Magellanic Cloud right here, just off the edge of the DES footprint. So it's the Milky Way's most massive satellite, and we found it has a really significant effect on the orbits of these streams. Okay, so for the final velocity component, the radial velocities, we've been conducting a spectroscopic survey led by Ting Li with the goal of measuring radial velocities and metallicities of stellar streams across the southern sky. So the survey is called S5, or the Southern Stellar Stream Spectroscopic Survey. We use AAT. We also use Magellan for some higher resolution follow-up. Prior to S5, there really was no systematic spectroscopic survey of stellar streams. And this was largely due to the difficulty of target selection. So streams are very diffuse, they're very stretched out on the sky. So it can be difficult to get sufficient time to observe all the member stars if you're not able to efficiently select likely target members. But by taking advantage of the very precise DS photometry and the new proper motion measurements from Gaia, we're able to much more efficiently select targets. And so far, S5 has observed more than 20 stellar streams. If you're interested in learning more, we have a website here, and you can check out the overview paper, which was led by Ting. Okay, so here's a figure from one of the other recent S5 papers that Ting led on our first dozen streams. So I mentioned S5 has observed more than 20, but here's a summary of the first dozen. So you can see, again, this is on the sky. We have the DES footprint here. We've been able to follow up a lot of those DES streams that I mentioned, and also some others across the southern sky. So this is really exciting. It's the first time we've had a population of streams like this with these complete 6D measurements. So we can use them to measure the galactic potential. We can look for gaps or perturbations in these systems, look for low mass subhalos, and we can also begin to study them as a population, which we weren't really able to do before. Here's just a list of many of the S5 papers I don't have time to talk about, but mentioned we have some interesting ones on stream perturbations, on really low metallicity stellar streams. But I do want to take just a minute to talk about one of our primary science goals, which is measuring the galactic potential. So in particular, I mentioned that we saw that there's evidence of perturbation by the Large Magellanic Cloud in many of these streams. And here's a movie showing one of these streams disrupting. You can see the LMC come in, and it really pulls the southern part of the stream off of its orbit. So without including the effect of the LMC, you would not be able to get this stream model to line up with those black stars here. Let me see if I can back up again. Yeah, so this is the data on the sky. You can see that we can nicely reproduce the data if you include the LMC, but if you don't, it's impossible to reproduce that. And the same is true for all the rest of these streams. So we've been able to model more of these streams to study the effect of the Large Magellanic Cloud. So you'll see it come in just a minute. Orange is the one that was in the previous movie, but for all of these, they have some effects that you might be able to see. So green's a bit offset here, brown, orange has a really big offset, one that's affected. But basically we're seeing, oh, the Milky Way.
What? Yeah.
Yes, we're using a version of the Macmillan potential. So what we do is we take and find the best fit out of those. So we allow for a little bit of variation, but we're not varying the Milky Way potential here. No, so this includes the Milky Way and includes the LMC right now. Yeah, so we've done some tests where you throw in additional structures like the SMC or Sagittarius and see how significant the effect of those are. And it's much less than the LMC. So for this particular project, we just included the LMC to get a good understanding of that initial. For the LMC, we're assuming it's a spherical Hernquist profile with a fixed mass. And I'm going to talk a little bit about the effect of that assumption in a bit. Oh, the Milky Way is spherical as well, I think. Do you know the Macmillan? Yeah, whatever the Macmillan model is. Sorry. I think it is. But we do have, so within S5, we've done some work also where we allow the Milky Way to flatten and have also fit that with some of these streams. But for this one in particular, where we were really focusing for the first time on the effect of the LMC, we just use that fixed Milky Way potential. Yeah.
But in principle, you would imagine that the LMC current is a while, but assumptions about the Milky Way.
Yeah, definitely. And that's something that we've continued looking into. And I have a couple of slides on that. Yeah. So just quickly, this is the sort of summary plot of this first measurement, the LMC mass with these streams. So here's the posterior distribution on the LMC mass for each of the 5 streams that I fit. And you can see they're in pretty good agreement with a relatively high mass LMC. And, this is great because it's the first time we've been able to use a population of streams like this with these consistent 6D measurements to make this sort of measurement of the LMC mass. But of course, as you said, there are a lot of assumptions that went into this. And so one is that we know that both the Milky Way and the LMC potential are deforming in response to each other as the LMC falls in. So this is from a paper by Sophia Lillingen that came out earlier this year, also from the S5 collaboration, where she studied the effect of the deforming LMC and Milky Way on one of these stream models. So she looked in particular at that one that I showed in the first movie that's being very significantly perturbed by the LMC. So here is just showing the density at present day of Milky Way, LMC, and then the joint potential from an n-body simulation. So she used basis function expansions fit to that simulation and included different components of those expansions to figure out what the effect is on this stream model. So here, this is showing, it's a little complicated, but here the x-axis is the position along the stream on the sky. The y-axis is the y direction of that position on the sky. The gray bars are the uncertainty on the measurements. And then here on the left, she's showing what happens when you have a fully live Milky Way potential, and then you include different components of the LMC potential. And on the right, the LMC is fully live, and she includes only certain components of the Milky Way expansion. So what she's seeing really is that the most important thing here is the dipole component of the Milky Way. So this is because the Milky Way is sort of stretching in the direction of the LMC as it's falling in. So this is really showing us that absolutely, if we want to get a complete understanding of the gravitational potential of the Milky Way and its massive substructures, that we do need to include more complexity in our models. And that's something that we're continuing to work on in S5.
So like dipole, does that include most of the center of that?
Yeah, so even in my more simplified fits, I do allow the center of mass of the Milky Way to move. That's the only thing that's changing in the Milky Way potential, and then the LMC is also moving. But she's also finding that the LMC is causing the Milky Way potential to kind of flatten and stretch a little bit, and that's one of the important components. Yeah. Okay, and then this is just to show the position of closest approach around the LMC of many of these streams. So this is essentially longitude and latitude around the LMC, and bigger points pass closer to the LMC. So these are some of the S5 streams, and it's just to show that we are probing various points around the LMC potential, especially Elky, which is our most distant stream, is on the other side of the LMC. And so we have a lot of information, and as we continue to detect more streams, and especially more distant streams, we'll be probing even more components of its potential, and we should be able to get a measurement not only of its total mass, but of its full asymmetrical profile. Okay, so for the rest of the talk, I mostly want to focus on these streams at sort of a population level. So this is the figure that I showed before, summarizing or just showing some of the streams that we've observed with S5. So now we have radial velocities, we have proper motions, we have distances, we have metallicities for all of these streams. So it means that we can infer a lot of their properties that we couldn't before. So we can determine which of these streams had globular cluster versus dwarf galaxy progenitors. We can determine the initial masses of their progenitors. We can determine their orbits. So Ting had a really nice paper that came out earlier this year where she summarized many of these properties. And I'm mostly going to talk now about comparison between this population of streams and a similar population of streams in the fire simulations. So fire simulations is a set of fully cosmological hydrodynamic simulations. Here's a nice movie of one of the Milky Way analogs in fire. So in particular, I'm interested in the Latte and Elvis on Fire suite of simulations. So Latte is zoom-ins of Milky Way analogs, and Elvis on Fire is zoom-ins of local group analogs. So they have Milky Way Andromeda pairs. It's a little difficult to see on this screen, but you can see that there is a lot of this substructure being accreted and disrupted. So for the first time, we're at resolution levels in cosmological simulations where we can identify dwarf galaxy streams around Milky Way mass hosts, so we can begin to make these comparisons with this new population of streams that we've observed in the Milky Way. Okay, so a lot of work has been done to study the populations of intact satellite galaxies in the fire simulations, and they've been found to be in pretty good agreement with observations of Milky Way satellites. So here's just a look at the cumulative stellar mass distribution. So the colored lines in the back are from some of the Elvis on Fire and Latte simulations. These are Latte, up here is Elvis on Fire. And then we have the Milky Way and Andromeda, and we'll mention that Andromeda is a little bit more massive than the simulated galaxies here, which could explain why that curve's a little bit offset. But generally, Fire does a pretty good job of reproducing the stellar mass function. Here's a look at the radial profiles, so just the distance from the host galaxy. Again, so here's different groupings where blue is all the hosts. This is the scatter between the simulations. Purple is the isolated hosts. So those are the Latte simulations, just a Milky Way. And then orange is paired. So those are the Elvis on Fire pairs. And then black here is Milky Way, and dashed is M31. So again, this is just to show that Fire does a pretty good job of reproducing the radial distribution of satellites as well. Yeah.
To Elvis, do they have the same resolution?
Elvis is slightly higher resolution. It's about a factor of 2 different.
Elvis was
Elvis is the pairs.
pairs,
Slightly.
it's higher res.
Yeah, slightly.
So there's a suite mini ensembles of both calculations. And the Milky Way-like ones are unconstrained except for what, the mass or something? What is it that makes a Milky Way something that will become a Milky Way in that simulation? How was it selected? It was
Yeah, so they select on the mass. They all have masses between 1 and 2.1 times 10 to the 12 solar masses, which could actually be a little bit higher than the Milky Way. And then there's some property of the disk that they select on as well. And then they try to also select some based on the accretion history to get LMCs, but actually none of them have LMCs at present day. Some of them have soon to be accreted or recently disrupted LMCs.
so the mere existence of the second big thing
Mhm.
along with the
Yeah.
that's going to change things. So have you seen the manifestation of those changes? Because just the existence of those two entities in the initial conditions
Yeah,
means that essentially all scales are affected.
yeah.
And so
I think
what they become is quite different.
Right. I don't think there have been very clear distinctions seen in the satellite populations. One thing that people in FIRE have seen is that the pairs seem to sort of form slightly earlier than the isolated ones.
Yeah.
Their satellite populations are a little bit
Yeah,
small.
I would have expected that. Yeah.
Yeah, that's the main difference that I'm aware of.
Yeah, because they aren't close enough to have done a lot of damage, but there would be an impact on the dwarf galaxies surrounding, presumably.
Yeah, yeah. And so I'm going to get to my work, which is mostly on the streams
Yeah.
rather than the satellites, but actually we don't see a very clear difference even
Oh,
in this. Yeah.
Do you want to take that one back with you?
A pretty good job of reproducing the intact satellites, but I think it's really important also now that we have this data on stellar streams to also include the population of streams that are undergoing tidal disruption. And this is both because it means that we're increasing our sample size, we're comparing more satellites between simulations and observations, and also because tidal disruption is a large source of uncertainty in these comparisons, and tidal disruption is very dependent on the density profiles of these systems, which is sensitive to both baryonic and dark matter physics. So by including streams, we actually get new information that we can use to constrain both galaxy formation and dark matter in our galaxy. Okay, so I've been focusing on comparing this population of streams in the Milky Way that I described to streams in the FIRE simulations. So last year, Nand Penetampesan, who's a grad student at UPenn, published a paper where he identified stellar streams in the Latte and Elvis on FIRE simulations. So this consists of 13 Milky Way analogs across the 2 suites. And he identified streams down to stellar masses of 5 times 10 to the 5th solar masses. So this doesn't cover the full range of dwarf galaxy streams that we've observed in the Milky Way just because of the resolution limits of these simulations, but it does have some decent overlap that we can begin to use to make these comparisons. Here's a figure from Nand's paper just showing some of the different systems he's classified. So here's one of the streams. Here's a system he classified as fully phase mixed, and here's a system that's classified as an intact satellite. So I'm happy to answer any questions about this. I won't get into detail on the classification, but it essentially depends on these 3 things: the number of particles, the maximum pairwise separation, so streams must be extended structures, and then the local velocity dispersion, which separates between the more phase mixed systems with higher dispersions and the coherent streams. And we did confirm all of this by eye, looking through these systems to make sure that we are doing a good job of selecting the structures that would be identified as streams if we observe them in the Milky Way. Okay. So the first sort of naive comparison you can make is just to count up the number of streams that come from dwarf galaxies in the stellar mass range that we see in the Milky Way and that we see in the simulations. And so at first look, the FIRE simulations have a higher number of high stellar mass streams. So they have a median of about 8, and they all have at least 3, whereas in the Milky Way, we have Sagittarius And then depending on the uncertainties on the stellar masses, maybe the orphan Chenab stream. So 3 to maybe another one, depending on stellar mass uncertainties. So here's a look at the cumulative stellar mass distribution in the Milky Way and fire. So blue here is the stellar mass distribution of streams in the fire simulations. The lighter blue is Latte, darker blue is Elvis. So they're separated both because they have slightly different resolutions. You can see Elvis goes down a little bit further, and just so we can try to see whether there is a difference between these populations in the isolated versus paired hosts. And then in black is the dwarf galaxy streams in the Milky Way. So these are all streams that we've observed with S5, but it actually does include the full population of Milky Way dwarf galaxy streams in this mass range, because even the streams that are in the northern hemisphere have been found to be associated with streams that have been observed by S5. Yeah.
What do you like fire simulations do you guys do?
These fire simulations, do you guys attempt to also match the assembly history of the Milky Way halo? You know, for things like the sausage, you know, coming in at like very high redshift, that sort of thing.
Not necessarily. Yeah.
That would impact this a lot, wouldn't it? Because I mean, like you're holding fixed like the stellar mass and the halo mass of the Milky Way, but if you change the history, that'll then change how many streams are present today, because these are transient objects.
Should, and that is one of the things that I'm interested in, and I've looked into a little bit, and we actually didn't see a huge amount of difference that's correlated with the accretion histories among these 13 hosts that we're looking at. But I won't talk about it now because it's very preliminary work, but we're also currently doing some semi-analytic modeling to see how the stream populations change when you change the accretion histories.
So how long do these streams persist as identifiable streams in your simulations?
It varies, but some of them for a long time. It depends on the orbits they're on. So it can even be like 10 gig years. You know?
Oh, wow.
Yeah.
And while we're asking questions, what fraction of the source of the stream is typically disrupted? The whole thing, or?
Oh, it varies actually. Some of them is what percentage of the stellar mass is in the tails versus the progenitor. Some of them it's very small actually. So one of the interesting things that we're seeing here that I will talk about is that a lot of the streams do have surviving progenitors, which is not really what we're seeing in the Milky Way. So the Sagittarius stream has a surviving progenitor, but among the dwarf galaxy streams, that's the only one. And so what we actually see is that also a large fraction of the surviving satellites in fire have tidal tails. So almost 50% of satellites that are picked up by the halo finder have been classified as streams because they have most of their mass still in the progenitor. So it still looks like a, surviving satellite, but they have maybe up to 10% of their stellar mass in like very extended, but very diffuse tidal tails. Yeah. But some of them have fully disrupted progenitor, so it varies. Yeah, and I also want to mention that we are using stellar mass values here that come from the metallicity measurements from S5. So these are estimates of the total stellar mass of the progenitor and don't require that we've observed the full extent of each of these streams because we don't necessarily know that we've observed the full length of the tidal tails. But of course, there is the question of whether we've observed all of the dwarf galaxy streams in the Milky Way, and the answer is definitely no, and that is one of the big parts of this paper that I'm going to get to. Okay, but first I want to show just a couple more versions of this figure. So here on the left is the same one. This is streams only. In the middle is intact satellites only. So these are the intact satellites that have no tidal tails. So it's not all the systems that are in the halo catalog of fire, but it's all the ones that are in the halo catalog and do not have tidal tails, are not classified as streams. And then on the right is the combined distribution. So you can see this is a bit more consistent, although there's still some inconsistencies that you can see here. Yeah, so like I mentioned, one of the big points here is that a lot of the surviving satellites in fire do have tidal tails and would be classified as streams. And so if you look only here, perhaps part of the problem is that some of the systems in the Milky Way that we've classified as intact satellites do actually have very diffuse tails that have not yet been detected and should be included in our stream sample. And this also suggests that when we make comparisons of satellite populations in fire, we should be including things like Sagittarius that have a surviving progenitor, even though it also has tidal tails. Okay, so I mentioned that we have not observed all the dwarf galaxy streams in the Milky Way. You might think that at these really high stellar masses, they would be very easy to spot. So something like Sagittarius is pretty easy to detect, but there's still a question of whether all of these fire streams would actually be observable. And so in order to address this, we create mock dark energy survey observations of these streams. So like I mentioned earlier, the DES data is really excellent for studying streams, for searching for streams. And so we use only the DES survey, although there are other similar surveys across other parts of the sky, like CCALs, SDSS, Pan-STARRS, STELV, but we only consider DES here because essentially we're saying if we had DES observations of all of these fire streams, and some of them are undetectable, and that's sufficient to resolve this so-called too big to fail problem in stellar streams, then if we did a more thorough estimate of the detectability in different surveys, that would be even more efficient in resolving this too big to fail problem. So in order to create these mock observations, we use Ananke. This is a code written by Robin Sanderson, which was initially used to create a mock Gaia catalog of the fire simulation. So here, the top is Robin's synthetic observations of one of these latte halos. At the bottom is the real Milky Way. So we've adapted this code to work with the DES photometry instead. And so essentially the way it works is you take the star particles from the simulation, which have ages and metallicities, and then you sample those into a population of star particles, assuming using an isochrone with that age and metallicity. And then we use a spatial and velocity kernel to spread them out in physical space. Okay, so then we estimate the detectability of these streams. So we use a methodology that's motivated by the search in DES. I mentioned to search for these streams in the dark energy survey, we're essentially picking out stars that we think are likely to be stream member stars, so they're old and they're metal poor. And we're looking at resolved star catalogs. We're not looking in images. And so we calculate the surface brightness of each of the segments of the fire streams in order to estimate their detectability using the same method that we would for the dark energy survey, if that makes sense. So we determine the surface brightness limit to be that of the DES streams, which is about 34 megs per arc second squared. This number is different from the surface brightness limit you would hear if you were talking about looking for streams in images. So this is specifically for these searches in resolved stars. And then we calculate the surface brightnesses of the streams in these 15-degree long segments so that we can consider parts of the streams to be detectable and parts to be undetectable. So here's just one example where most of the stream is detectable, it's red, and then there's this more diffuse component here that's not detectable. We also have some streams that are fully detectable or fully undetectable. And another important point is that I mentioned that many of these streams have surviving progenitors. So we independently estimate the detectability of the tidal tails and the progenitors. So for this analysis, we mask out the progenitors, and then we look at all of the surviving satellites in fire, including the stream progenitors, and we estimate their detectability using an analytic prescription from Derlica-Wagner et al. 2020. So this is based on observations of the Milky Way dwarf galaxies, and it just depends on the total luminosity, the half-light radius, and the distance of these satellites. So here, blue systems are detectable, green is undetectable, and the triangles here are the stream progenitors, and the circles are the fully intact, undisrupted satellites. So you can see most of the satellites in the stellar mass range are, in fact, detectable. But many of the streams actually are not. So this figure summarizes the number of detectable streams in fire. So here, each bar represents one of those 13 Milky Way analogs, so it's a different simulation, and they're ordered by the host halo mass, the total mass. So M12R is our least massive, and Romulus is our most massive, so about 1 × 10⁻12 to 2.1 × 10⁻12. In the background here, this line in the gray shaded region is the number of Milky Way dwarf galaxy streams in this stellar mass range. So we have 2, and then the uncertainty there is just due to the uncertainty on the stellar mass measurements. So you can see that when we look at the total number of streams, which is the full height of these bars, it looks like there's an excess of high stellar mass streams in fire. But when we consider detectability, which is the dark blue segment at the bottom, these are the streams with detectable tidal tails, it's actually much more consistent with what we see in the Milky Way. So this is telling us that perhaps if fire is correct, there's a population of very high stellar mass but low surface brightness streams that we've yet to detect in the Milky Way. In the middle, the sort of medium blue are the streams that have detectable progenitors, but not detectable tidal tails. So the other important point here is that FIRE is actually predicting that there's a fairly large number of systems in many of these Milky Way analogs that would be detected as intact satellites, but have very low surface brightness tidal tails that might not yet be detectable. So perhaps some of the systems that we're studying as intact satellites are in fact stellar streams. Okay, so this is the same figure that I showed before, these stellar mass functions for streams, intact satellites, and the combined distribution. And we can make these same plots, including only the detectable systems, and they look like this. So you can see it's much more consistent. The number of streams is quite consistent within about 1 sigma. There is a slight excess in the local group simulations specifically. So these are the paired Milky Way Andromeda analogs. But overall, it's pretty consistent compared to what we saw here.
Politically, 1 sigma, but locally it's 100 and not.
Yeah, it's true. Although I don't know if you can see for latte, it's actually down here. So it is interesting. This is one place where we're seeing there is some difference between the local group pairs and the isolated Milky Ways. Yeah, and one other possible source of uncertainty is the way that we've calculated the stellar masses. So we're assuming a mass metallicity relation at a redshift of 0, whereas we know these systems were accreted and disrupted a bit earlier. So it's possible that their masses are slightly higher than what we've included here. So that's one way that this could be improved in the future. You can also see that the intact satellites are much more consistent here. And then the combined distribution of streams of intact satellites is much more consistent. And so I do want to point out that for this panel here, I don't only remove intact satellites that aren't detectable, but I also include streams that would be mistaken as intact satellites. So the systems in those middle bars in the previous figure, where they have tidal tails that are undetectable, but they have a detectable progenitor. So they would be mistaken as intact satellites.
The Milky Way and the satellites, does the LMC make up the candidate?
Yeah. Yeah.
Just pick the one off there.
Yeah. And like I mentioned, none of the latte or Elvis on fire simulations have LMCs at present day. So it would be interesting to do more of a detailed study of analogs with LMCs. Yeah. Okay, so we can also estimate the detectability of these systems in the future. So LSST with Rubin Observatory is going to be really great for the discovery of stellar streams. It's, you know, a improved version of DES in terms of stream discovery. So it's going to cover more of the sky, more precise photometry to deeper magnitudes. So in order to estimate this, we reran the same mock observations, but using Rubin photometry. And then this figure is showing the number of detectable streams as a function of that surface brightness limit. So for DES, we determined it by looking at the surface brightness of the streams that we detected in DES and found that the limit is 34. For LSST, it should be fainter, but without real data, it's really difficult to figure out what that precise number will be. But essentially, as we start to detect streams in LSST and figure out down to what surface brightness we can go, we can say, you know, if we're at a surface brightness of 36, then we expect to see about 5 of these really massive streams in the Milky Way. And if we don't, then that's suggesting there's some interesting discrepancy between the predictions of the fire simulations and what we see in the Milky Way. Another prediction is for tidal tails around satellites. So here I'm showing in distance bins, so the distance from the center of the host galaxy, the number of satellites with detectable tails, undetectable tails, or no tidal tails. So dark blue are the ones with detectable tails. The middle blue are ones that have tidal tails but are undetectable, so would be mistaken as intact satellites. And then this lightest blue is the number with no tidal tails. And the error bars here are just the scatter between those 13 simulations. Here on the right, it's the same thing, but just looking at the fraction of the total satellite population in each distance bin. But I think it's interesting here, you can see that there's actually a very large fraction that's predicted by fire that would have undetectable tidal tails. So this means that fire is suggesting that many of the satellites between 50 and 200 kiloparsecs are predicted to have tidal tails that are just very low surface brightness with a significant amount of scatter. I'll just point out that 2 systems that we do know of in the Milky Way that would fall in this category of having a surviving progenitor, but being disrupted in the stellar mass range are Sagittarius, which is in this distance bin, Antlia 2, which is a disrupting dwarf galaxy, doesn't necessarily have very clear extended tidal tails, but is in this distance bin here. Okay, so this number and stellar mass function of streams is very consistent, looks great. There's no too big to fail problem in stellar streams, but there is one really important discrepancy in the orbits of these systems. Yeah.
Said that last bit quickly.
Sorry.
And it's interesting. So Sagittarius is our, I mean, big, after the cloud, Sagittarius is the thing that we put so much hope in terms of the potential and in terms of, do you think that's another important sort of cosmological constraint or important merger history constraint on the Milky Way? Is that actually you would get, you know, is it rare to get a Sagittarius-like system? What are your thoughts on that? Because you know, I'm not sure if it's not a big deal or if you think about it more, because it's interesting.
Yeah, I think what's interesting that we're seeing here actually is that many of these prior simulations have more Sagittarius type things than we're seeing in the Milky Way. So there's just a large number of these really high stellar mass, so above 5 times 10 to the 5th up to about 10 to the 9th streams that have surviving progenitors, and you know, some of which should be detectable, some of which should not be detected. Whereas in the Milky Way, we're seeing Sagittarius.
Is that because of something special about the Milky Way compared to the way you've done the constrained realization? So, you know, in other words, is that telling us something about our cosmological formation history, that it's not just these two things, there's something deeper about the overdensity that we came from?
I think it's possible. I mean, so I think that as we continue to get deeper observations and detect more streams, that discrepancy could become stronger, or we can see maybe they're just low enough surface brightness that we weren't able to detect them yet. So I think right now it's hard to say, because we are estimating that many of these systems in fire should not yet be detectable, but with LSST we should be able to see most of them, I think. So if they're not showing up, then that tells us something interesting about the Milky Way's accretion history or some property of the Milky Way and how it's disrupting systems. I mean, I'm going to get to this other discrepancy in the orbits now, which I think is also really interesting and could tell us something unique about our galaxy, or could be telling us something about our simulations. Right. Yeah, so I think it's an important thing to keep in mind, but it's hard to say right now what the significance is. Yeah. Okay, so we also modeled the orbits of these systems to measure their pericenters and apicenters. In the left panel, I'm showing only the detectable streams, and the right panel is all of the streams. That's the only difference between the two panels. The Milky Way systems are these X's down here. The x-axis is pericenter, y-axis is apicenter. And then the circles and triangles are the fire streams from the 13 analogs. So the triangles are streams with surviving progenitors. The circles are streams with fully disrupted progenitors, just tidal tails, and they're colored by the look back time and accretion history. There's a lot of pieces here, but darker means they were accreted earlier. Lighter means they were accreted more recently. So you can see there's a bunch of dark ones here that aren't detectable here. Maybe that means they've been more phase mixed or more diffuse. There's also a lot of these more distant ones that are not detectable here. So this is telling us something about these predictions for the undetectable streams that could possibly exist in the Milky Way. But a very important point here is that even when you look at the detectable systems, there's a clear discrepancy between these orbits of the Milky Way streams, the X's down here, and the fire streams. So you can see that fire is disrupting systems at much larger pericenters, and it actually has no systems at these smaller apicenters within about 50 kiloparsecs, which is different from what we see in the Milky Way. So in fire, we measure these pericenters and apicenters by tracing the position back through the snapshots and then integrating in the simulation potential around pericenter. And we're measuring the most recent pericenter and apocenter, which should be most consistent with what we're able to measure for the Milky Way. For the Milky Way, we measure the stream orbits by integrating them using the 6D information that we have in a static potential. But I have done tests to see what happens to the fire orbits if you integrate them in a static potential, and it is not enough to resolve this discrepancy that we're seeing here. And I also want to show, I think it's probably very difficult to see here, but this is just a sample of the morphologies of some of these systems. Here I'm binning them by stellar mass and by pericenter. So the main point I want to make here is that if you look at the systems down here, which all have pericenters of more than 82 kiloparsecs, they are all extended streams. So these aren't just, dwarf galaxies that are maybe have a couple stars and a tidal tail. Like these are very low surface brightness, so it's a smaller number, but they're very extended still. They look kind of like this, but with fewer stars. So these are proper streams that are forming at these large distances.
And again, actual position instead of apple and pear. They're all in between apple and pear, right? So it's the same plot as the actual position. You still have the same discrepancy.
Yes. Yeah, I think you would.
You got that calculated. That issue.
Yeah, right. Although for some of them, it's difficult to define what the exact position is because they're very extended. So if we're looking at the ones that have surviving progenitors, we can use that as the current distance. But for some with very long tidal tails, it's
Is the clumping of the material along some of these tails physical or numerical artifact?
sorry, I missed the beginning.
Is the clumping of the
Some
along the
of it
tail, is
Some of it is from how we do the mock observations where we're sampling in. So because you're splitting up the simulation star particles into individual stars, we use this spatial kernel to split it up. You get some of this clumpiness, but we have done some tests on varying the kernel and to make sure that this clumpiness isn't affecting the results here. But I do think that if you want to use these mock observations to do something more precise, like looking for gaps or measuring the velocity dispersion, a little bit more complicated. This is the point about independent versus dependent potentials. But basically, you can see that the points are connected by two lines, which are the same streams modeled in dependent versus independent potential, have pretty similar pericenters and apocenters, and it's not enough to resolve the discrepancy between simulations and observations. Here's another look at the orbits. So this is pericenter on the left, apocenter on the right, looking at systems at different stages of disruption. Yeah.
Solution that maybe your Milky Way is your Milky Ways are too massive?
It's possible. Yeah. So I do think so the lowest mass one is right around 1 × 10⁻²⁰, and the Milky Way is probably a little bit less massive than that. So one of the things that we are interested in looking at now is actually varying the mass of the host galaxy and seeing what effect that has on the orbit. So that's one possible explanation.
Just to follow up on
Yeah.
that, have you guys also done a position convergence study to ensure that
That's another thing that we're working on. Yeah, so within Fire, we have triple latte, which some of them have finished running very recently. Some of them are still running. So we haven't identified streams there yet, but that's 8 times higher resolution. So I'm definitely interested in doing the same sort of study and comparing there. I've also been looking at the Riga simulations, which have simulations that are similar to the resolution of latte, some that are slightly lower resolution, and one that's at the level of triple latte. So my preliminary result there, which is pretty early, is that I'm seeing the same thing in Auriga, and the orbits do change slightly when you look at the higher resolution, but not necessarily enough to resolve the discrepancy we're seeing here. But that's still a work in progress and something we're definitely looking into. Yeah. And I'll show a little bit more detail on some of those systems, but a lot of them are these sort of systems with surviving progenitors with a small fraction of the mass in their tidal tails. And it could be partially due, so only looking at Fire, it could be partially due to the fact that Fire tends to have larger sizes for its galaxies, and they have kind of these extended stellar halos. So it might just be the outskirts that are being stripped a bit, and maybe we don't see that in the Milky Way, but yeah. Yeah, there are some circles that are pretty far out, but here you can see they're mostly triangles at the largest pericenters. Yeah, but even that far. Yeah. Yeah. Yeah, and right. Yeah, so there are some preliminary resolution studies in fire, not with this stream specifically, that suggest that they're not being numerically disrupted, but that's definitely something I want to look into in more detail. Yeah. But this is just to show that, so, oh, sorry, yeah.
One possibility is the mass, the other possibility is the resolution, but it's also possible like the way how fire or Auriga or the simulation dealing with the disruption rate or like the disruption from the disk is like over disrupting. So what we are seeing here at 20 kiloparsec stream, but it's in the simulation is fully phase mixed. So we don't see them, while the one we are still seeing intact at like 100 kiloparsec, but in the simulation we are a stream. Is that possible?
Yeah, right, that is possible, and that's part of what I'm showing here. So this is the green histogram is the seismic systems in fire, the streams, and purple is surviving satellites. So like Ting was saying, we are seeing that the distribution pericenters and apicenters of the phase mixed structures in fire is more similar to the streams that we see in the Milky Way, both in terms of pericenters and apicenters. So it could suggest that fire is over disrupting. Another possibility is we do kind of see when we look at these phase mixed systems in fire that some of them have, you know, they look very phase mixed, very diffuse, but they'll have some slightly more coherent components that, you know, when you create mock observations could appear as streams. So maybe some of the Milky Way streams are part of these slightly more phase mixed structures. But it's hard to tell. And there's a lot of possible explanations from this that I will talk about just a little bit. But I wanted to show this plot last figure. Just looking at some of these systems. So this is looking at the satellites with and without tidal tails in fire, looking at their pericenters on the x-axis and looking at the density within their half-light radii. And so this is the average density of the host galaxy at this distance along the x-axis. And so systems on this side should have a tidal radius that's smaller than the half-light radius, roughly. And on this side, the tidal radius should be larger than the half-light radius. So you would roughly expect systems on this side of the line to be disrupting and systems on this side to not be disrupting. And here I'm coloring the points by the fraction of stellar mass that's in their tidal tails. So yellow means that has a very large fraction that's disrupted, although everything here still has some form of surviving progenitor. And purple means that very little fraction has been disrupted. And the big circles are the ones that are classified as streams. The little circles are intact satellites. So you can see that there is a trend here that you would expect. So the systems that are more disrupted are further down in this space, but we are disrupting systems in fire that are up here. And that really is because the stars that are forming the tidal tails of these systems are really at the outskirts. So they are outside of the tidal radius. It's just there's sort of these extended stellar distributions in some of these satellites, at least the ones that are all the way up here, that are forming these very extended but very diffuse tidal tails. And I think that we don't know right now whether something similar is happening in the Milky Way because these are just such low surface brightness structures with a very small number of stars.
Present day or
It's the present day. Yeah. So this, right. Yes. Yeah. Right. And so the way that I produced this was also using the mock observations to make it fully analogous to similar figures with Milky Way satellites. So we create the mock observations, use the same code that we use to fit the structural parameters of observed Milky Way satellites to get the half-light radius. The density comes from the true mass from the simulations. Yeah. So this is present day because it's same as the observation. Okay, so just a little bit of discussion of some of these possible explanations for this discrepancy that we're seeing. So one, possibly resolution. I don't have answers for you about any of these possible explanations yet, but I just wanted to talk about some of the things that we're interested in looking into next. So in terms of resolution, we're definitely planning on doing some studies of these stream populations across resolution, both within fire, looking at triple latte, which is 8 times higher resolution than latte. And then also I mentioned I'm looking at Auriga. It's possible that the fire feedback models are contributing to this possible over disruption. So we know that it's a pretty aggressive feedback model that introduces some puffiness into galaxies. So within fire, there have been resolution tests to see whether the sizes of the galaxies are resolved. And in these masses, they mostly are. At the lower end, possibly, they could be artificially large due to resolution issues. But at the higher masses, we're seeing that regardless of resolution, they have sizes that are larger than observed Milky Way satellites, which is probably due to the feedback models. So that's why it's interesting to compare to other simulations like Auriga that have completely independent baryonic feedback models. And so we can see whether that could be partially responsible for some of this over-disruption that we're seeing. Another important question is whether it's actually properties of the host galaxy. So we've had some discussion of this already. Is it, the total mass of the Milky Way, some properties of the Milky Way disk, or of the accretion history of the Milky Way? So in order to address this, we're both doing sort of a deeper look into the differences between some of these simulated galaxies and the cosmological simulations that we're considering. But also we're working on doing some semi-analytic modeling to see how properties of the stream population change as you change these properties of the host halo. And then another thing that will be really interesting is with upcoming observations, we'll be able to detect many more streams around other galaxies besides the Milky Way. So with Rubin, with Roman, we expect to see many extragalactic streams. And so it'll be really interesting to compare populations of streams in our real universe around different galaxies and see if we can learn something about how they vary as you change properties of the host galaxy. And then there's the question of whether dark matter could be affecting it. So I think it'll be interesting at the same time as we're exploring all of these properties of our simulation and baryonic physics and properties of the host galaxy. There are also cosmological simulations run in alternative dark matter models. So FIRE has SIDM simulations and dissipative dark matter. So we're also planning on looking into those and identifying streams to see the effect of changing properties of the dark matter particle on the resulting stream population. Okay, so I'll leave my summary here, and if there are any more questions, I'd be happy to answer them. Thank you.
So before going into questions in the room, I just wanted to check real quick and see if there are any questions online. Otherwise, going once, going twice. Okay, so Chris.
Well, did I hear you correctly that dwarf galaxies in the FIRE simulations tend to be too large?
Some of them, yes.
So surely before one gets into detailed modeling of the streams, shouldn't one try to nail that down? Because, much of what you get out is going to depend on that.
Yeah, I think that's true. But that's also part of why we're interested in looking into different simulations. Yeah, so as people are also continuing to work on the FIRE simulations and improve that aspect of them, so looking at other models, yeah.
Gina?
I love these streams, and I'm wondering if you've thought about, you've kind of separated things from an observational perspective into, okay, this is a stream, this is a surviving thing. And have you thought about if you could have a measurement of every star in the Milky Way and local group, what metric you would use to understand and map this to cosmological parameters or, things about the Milky Way's potential, what kind of, instead of just relying on the streams, what would you do with that map?
Really an interesting question. Yeah, so you mean even apart from just looking at individual systems, how would we map all of it on? Yeah. Yeah, I don't know. I mean, I think being able to associate them with different systems is interesting so that we can map them on to sort of when they were created and sort of what they've experienced as they've been disrupting. So both like the overall accretion history of the galaxy and the evolution of the galaxy as they've been disrupting. I don't know. I mean, I think it's definitely true that we need to move from just looking at intact satellites or just looking at streams or even just looking at like phasmic substructure in the stellar halo to looking at everything together, because we're seeing even in this work that it's all sort of a spectrum and it's very difficult to divide them up. So yeah, I don't have a great answer, but I think that that's a really interesting avenue. Yeah.
Nobody has a good answer, by the way.
Yeah.
risk framework for
Yeah.
that. And I think that's exciting opportunity to even think that way, because
Mhm.
of course, the state of the art is still, you know, individual streams.
This is really just a comment to Juno. I think really all the Nora showing here, right? Basic just use like for the objects, so it's really the kinematic 60 data. I think we use MATLAB a little bit in terms of to get the progenitor mass. But I think to answer your question, I think the next decade, if we want to say get every single individual star on the sky, I think chemistry is the right way of going. And I think that's something we haven't used. Also probably don't trust the simulations chemistry either, but I think that's kind of something we should think about, how we make that direction goes better, and also the observations better, and maybe that's something we should be able to compare, because no matter how the stars are perturbed by external subhalos, their chemistry shouldn't change. So that's something should keep in mind. I just want to add that.
All right. If there's no further questions, let's go ahead and thank Nora again